Okay, so today we're going to cover how we actually calculate state changes. So where we left off on Wednesday is we derived expressions for du is equal to c sub v dt plus t, all sorts of fun calculus terms. Question?
Could you lower the screen?
Oh, yeah. I guess I can do that. Let me just get this here before I mess it up. And the last one was ds. So what we're going to talk about is how do we actually use these equations to accomplish something useful. So from the homework, the hope of homework 1 is basically to emphasize, yes, it'd be really nice if we had entropy, enthalpy, internal energy all calculated and tabulated for every different circumstances that we have. So for steam, we use water a lot, so it makes a lot of sense to put down extensive tables. But for the whole gamut of all the other compounds that chemical engineers may or may not work with, it doesn't make sense to have a steam table for absolutely everything, right? Because that would just be an enormous amount of experimental measurements that is not feasibly sort of possible to accomplish. So with these expressions here, we have ways that we can now calculate what is S, H, and U based on changes in temperature, pressure, and volume. That gives us a way that we can calculate everything that we need to know. So what we need in order to apply these equations are, what we need? Well, we need C sub P or C sub V data, or C sub P as a function of pressure and temperature, or C sub V as a function of V and T, or C sub V as a function of P and T, and so on and so forth, right? Heat capacity is not special. All thermo variables are functions of every other thermo variable. So if I change one thing, I have to change something else. There's no way around that. So with heat capacity, it is a function of pressure and it is a function of temperature no matter what. C sub P and C sub V. But when we look in the back of the books, it's only tabulated for ideal gases, and we'll tell you why that's really important. The second thing we need is we need an equation of state. And for an equation of state, basically what we need is we want volume as a function of temperature and pressure, or pressure as a function of volume and temperature, or we need to calculate dV dt at constant P, and dP dt at constant V. Right? These are all expressions that popped up in those equations on the last slide. Right? We all need to know basically how do the thermal variables relate to one another so that we can substitute them into the different mathematical relationships, integrate them, and actually get to an answer of what is S, what is U, what is H in all these circumstances. Okay, so for an equation of state, this is something that I think we're all somewhat familiar with. Ideal gas law, van der Waals equation, Peng-Robinson, SRK. There's more advanced equations of state for more specific applications as well. But for all of those, they have a couple of tunable parameters, but the idea is you tune those and then you kind of leave them alone. So we're not going to talk too much about equations of state, well, at all in the class. We'll use them quite a bit, but we're not going to go through the derivations of them or whatnot. They're just going to be things we're just going to grab off the shelf. Right? They're tuned, designed for particular applications and different purposes. Some of them are designed for oil and gas, some of them are designed for water, so there's strengths and weaknesses to all of them. But in general, a cubic equation of state is fairly good at describing gas or supercritical fluid behavior. There's no equation of state, unless it's extremely specialized, that describes liquid behavior well. But for our purposes, an equation of state here, so this number 2, just we'll grab it off the shelf. Whatever we feel like is going to be the easiest or most appropriate or most accurate to use, we're just going to grab one and use its math. But for C sub P and C sub V, the question is, right, we need heat capacity, because there's no way to predict it, for every function, every temperature and every pressure that we possibly could conceive of. And again, that doesn't get us over this main problem of, why don't we just have steam tables for everything? So if we have to have a heat capacity at every temperature and pressure, well, what good is it? But instead, there's an alternative strategy. So what we can do is we can get expressions for how C sub P changes as a function of pressure, and I guess more like it, how the heat capacity changes as a function of volume. And we'll see why this makes sense in a little bit. So the idea then is we'll first measure the ideal gas heat capacity. Right, so either C sub P star is typically what we use for this in the book, or C sub V star. This is the ideal gas heat capacity. So an ideal gas occurs when pressure is equal to 0 or the specific volume is infinite. So the notion is that maybe we can get by with only measuring the heat capacity of an ideal gas, or with StatMech only predicting the heat capacity of an ideal gas, then using an equation of state to calculate how it changes as a function of pressure or specific volume. That way now we've reduced everything down in thermodynamics to basically 2 things: ideal gas heat capacity and a tuned equation of state for our particular compound. And from there, we can calculate everything. All the phase behavior, any Rankine cycles, piston cylinder devices, basically with 2 sets of data. 1 correlation for heat capacity and 1 equation of state. So we won't really be using this too much, but as an example, it's a useful thing to go over so we can kind of revisit thermo math. Because this pathway is, as you'll see, is kind of a pain. So if we take du, which is equal to C sub V dt, plus this big derivative thing, we can relate this to an expansion of du with respect to t and v, which is just du dt at constant v dt plus du dv. So all we've done is we've just expanded using the chain rule, du, and then we've related it back to the combined first and second law. So as a reminder, this expression is just rearranging the combined first and second law of thermodynamics, playing around with a little bit of calculus, and this expression here is just the chain rule of of calculus. Just a recap of where we got it. So with this, we can play around with partial derivatives, and remember that the order of derivatives doesn't matter. So what we can say then is that we'll take the derivative d dv at constant t of du dt at constant V is equal to Right, so I'm just swapping the derivatives. So if we substitute in our combined first and second law, now we have an expression for dCV dV at constant T. Right, so how does the heat capacity change as I change the density of the fluid, right, or the volume of the container that it's in? Then this is equal to d dt. Oops. So all I did was I just substituted this into here, and that is the same thing as there. So if you work out the math, and remember, everything's a function of everything else, so that means that this dt, if I apply it here, I have to use the product rule. But it works out quite nicely that it simplifies down to a really convenient little expression. So again, if we have an equation of state, we know how the heat capacity changes from an ideal fluid to a real fluid. But it's not a very pleasant derivative to work with. I personally don't want to take the second derivative with respect to temperature of like the Peng-Robinson equation of state. That would be very unpleasant. But the great thing with thermo is that the whole process is pretty algorithmic. So that's why software packages like Aspen or other thermofluid simulators can really do these things very quickly and easily, because as soon as you've taken that derivative once and you've confirmed that you've done the math right, it's A-OK. But in class for homework, it's, well, not my first pick of something to do. Likewise, we can do the same thing by expanding dH, and we can come up with d C sub p dP at constant T is equal to minus T d squared V dt squared at constant P. So we can do the same thing with heat capacity, or C sub P. Okay, so now let's say we wanted to apply this. We wanted to know what is the heat capacity of a real fluid not in the ideal gas state. So what we would want to do is we would integrate from P1 at constant temperature to P2 at constant temperature, the heat capacity. And this would be C sub P of P2T minus C sub P of P1T. So then we would just substitute in our expression and work through the calculus. P1T to P2T. So not only do we have the pleasure of taking the second derivative of our equation of state, then we get to go around and integrate it with respect to a different variable. So if P1 is equal to 0, then C sub P of P1 is equal to C sub P star, which is equal to the ideal gas heat capacity. So if we're not going to run through the math, obviously, because we don't have an equation of state that we're actually using, but the heat capacity at any pressure for a real fluid, again, we have done no assumptions at any point up to this point here, is just the heat capacity of the ideal gas, which is not a function of pressure, because we've either defined the pressure or we know that the assumptions are valid. And we have our expression. And we can work through the same thing we wanted to with C sub v. But I'm not going to bother because we're never going to use this expression. There's a better way. So if we wanted to, we could calculate the heat capacity at any point in time, or sorry, at any point in pressure, temperature, space. But because U, S, and H are all state properties, we can choose a path that is much, much more pleasant. We don't have to choose this arbitrary path where we have to then determine what is the heat capacity at every point in real space. So instead, we are going to be a little bit more clever about it. So what we'll do is I'm going to draw a big drawing here in PT space. And we want to know what is the change of state properties going from P1 and T1 to P2, T2. We're going to go over two examples. So we could, in theory, try and go straight there. But then we're changing temperature and pressure at the same time, and so when we have that big, nasty expression for dH, for example, that means we can't simplify it down at all. So that one is really, we'll just rule that one out straight away. So instead, we're going to choose two different paths. One is the more direct of the two. We'll do a isobaric and then isothermal process. I'll actually call this one 2A and 2B. The other option is we choose a path that adds an extra leg where we go depressurize down to 0, heat it up, and then repressurize back here. And that should be a straight line. Well, best I can do. So I'll call this 1A, 1B, and 1C. So which of these two paths do we think is going to be the easiest? 1 or 2? Definitely 1. It's 3 steps, but you'll see why it's so much easier. Because in 2, this is a real fluid the entire time. There are no approximations or any simplifications. There's nothing we can make. In path 1, we go through an ideal gas state. So at pressure equals 0 here, this is where we have an ideal gas. And at all the pressures between here, this is where we have a real fluid. Who's not the best? Okay, so let's actually draw this out then. So if we're going to calculate the enthalpy, we know that dH, okay, a reminder, this is the combined first and second law. No assumptions, and how we got here, right, is when we basically substituted Q from the entropy balance into the energy balance, and then did some calculus. C sub P dt plus we'll break this into steps. So the first step, 1A. go back really quickly. What approximation can we make on step 1a to simplify our expression? What are we holding constant? We're holding temperature constant. So that means dt is equal to 0. So in this case, dH for step 1a is just equal to V minus this big long expression. We've eliminated one of those two terms. For 1b, go back really quick. What is held constant on step 1b? Pressure. And what else is special? Ideal gas. So now, in this case here, dP is equal to 0. So our dH is just equal to C sub P star dt. And then lastly, 1c is exactly the same thing as 1a, but just with a different state. So if we put it all together, we can calculate that the delta H of a real state change, real fluid, going from P1 T1 to P2 T2, we just add all the three steps together. So we integrate from P1 T1 to P equals 0 T1 plus from P equals 0 T1 to P equals 0 T2 plus from P equals 0 T2 to P2 and there we have it. So this is why ideal gas calculations are a lot more fun. So what we would do if we were to substitute an equation of state, right, like the ideal gas law, if we were to substitute this expression into this equation here, we would find out that it all cancels out. Thankfully, very conveniently. So in ideal gas, the heat capacity, the enthalpy and internal energy are not functions of pressure or specific volume. And it works out so nicely that all of these terms just magically balance out so they 100% cancel each other out. But for any real fluid, like van der Waals, which is the most complex that I'll make you guys do in class by hand on these types of calculations, right? Van der Waals does not cancel out to 0. You'll have a lot of lingering terms left. But the van der Waals is not very, accurate, but it's good for a useful exercise. So this is how we know that ideal gases, right, the enthalpy and internal energy are only functions of temperature, because we've taken these big long form calculations and then we've basically substituted in the equation of state, and we see that it goes away. There is no dependence. So regardless of what pressure you're at, if it's an ideal system, you just integrate with respect to temperature. So with respect to problem 5 on the homework, don't worry about, just only worry about temperatures. Don't worry about pressures or anything like that. Just assume it's an ideal fluid. Okay, so let's go example. If we choose path 2, so as a reminder, we don't get to have the opportunity to go to an ideal gas state. So everything that we're working with now is a real fluid on path 2. It's just 2 steps though, so it's fewer steps, but we'll see where it becomes less pleasant. So in path 2, we have step 2a, dH is equal to C sub P dt. Now this is not C sub P star. This is real fluid heat capacity. This is going to be the integral of P1 T1 to P, P T2 of C sub P star minus I barely squeezed on there. Double integral. Because in essence, what we're doing here is if we draw this out again on our PT plot, going from here to here, as we move along this path, we're basically having to do the same thing we were doing anyway. But for every point in space, we have to go down, over, up, down, over, up, down, over, up, down, over, up, because we have to know how does the pressure affect our heat capacity at every path along the way. So this section here is effectively calculating all of these moving up here. Then this section here is marching along that way. So in essence, we're doing the same amount of work, but the math is clearly much uglier here. And then for step 2a, it's just the same as before. Or sorry, 2b, it's the same. You just, instead of going from pressure equals 0, you're starting off here at some arbitrary pressure and then just finishing the job up there. So for the homework, right, so you're only having to worry about temperature changes at a constant pressure. So your job on homework question 5 is to develop a enthalpy and entropy table for saturated toluene from 0 to 110 degrees Celsius. So you have liquid heat capacity correlative data and vapor heat capacity correlative data. So just to go a quick example, in the data that you're given on the homework for number 5, you're given that C sub P over R is equal to A plus BT plus CT squared. So if you're going to calculate a delta H is equal to integral from T1 to T2 of C sub P dt. Just do a little rearranging here. So now we have an expression for the heat capacity as a function of temperature. So one thing to remember, this type of data here, there is no elegance behind it. It is just a polynomial fit to real measured data. There's no magic. So if this correlation tells you that this needs to be in degrees Kelvin, it has to be in degrees Kelvin. If it tells you it's in degrees Celsius, it has to be in degrees Celsius, because it is no more than just a correlation. So whatever the person who developed that correlation used, that's what you have to do to get out of it. Right? It's just like going in Excel and going, add tread line, second order fit. Oh, that didn't work. Third order fit. Oh, good enough. There we go. Put the data in the paper. Right? So that's what this is. It's a correlation, no more, no less. But the reason why it's a polynomial correlation, which is arguably a really bad correlation, because it provides artifacts sometimes, like maximum and minima, which are not theoretically allowed, but they don't introduce too much uncertainty. But the reason why people like to use a polynomial is because it's super easy to integrate. So the notion behind all of this, then, is that we just substitute in the expression. Integrate from t1 to t2, a plus bt plus c t squared dt. Yeah, I'll just put a little prime there or something like that so I don't have to bother with it. Some correlations have the r, some don't. It just depends on what the actual correlation is. So another way we could do it too is we could just get rid of that and then just put an r out front here. So integrating this is hopefully trivial. It'll be r times a times t2 minus t1 plus b over 2 t2 squared minus t1 squared. Note, it's not t1 minus t2 squared. It's t2 squared minus t1 squared. Plus c over 3 t3 cubed minus t1 cubed. And then you've calculated delta H.
You're down the homework, we just like show the top expression and just put it into a calculator and say top expression equals this.
So basically for this type of work here, if you just write this out here and then say you integrated it, I'll trust that you managed it just fine. Yeah. So in these problems, do as little by hand as humanly possible and rely as much as possible on MATLAB or Excel calculations. You had a question?
So what is the function of the reference temperature? You have said 0.01 degrees Celsius.
Right, so the reference temperature is a great question. So delta H is equal to H2 minus H1, right? And then H2 is at temperature 2, H1 is at temperature 1. So what's convenient to say then is I'm going to say that H minus H ref is what I'm trying to calculate. So if I set my reference enthalpy to 0, that means my H is equal to my delta H.
And that's for the 0.01 Celsius, or the 0.1 Celsius, we want that to be at 0.
And
correct.
And enthalpy will be 0 at that point.
Yes, enthalpy was 0. It doesn't have to be. You could set it to 100 if you wanted to, and then it just shifts everything by 100. So the thing to remember, right, is that we don't have a way to calculate any of these properties absolutely. And it doesn't make any sense. So for example, if I wanted to know, if I had a jar of air at a particular temperature and pressure, how I consider the energy in that jar is totally dependent on what I'm actually doing. If it's a nuclear process, then I could consider the energy stored in the nuclei if I exploded it, right? But that's not very useful to us. Do I care how much energy is contained in here if I cool it all the way down to absolute 0? No, not really either. All I really care about is how much does it take to heat it from, let's say, 0 to 500 C, or some range of temperatures that I actually care about. So instead of actually bothering with what the absolute amount of energy in the system is, all I care about is how much energy does it take to change that jar from one point to another point. So that's why reference states are extremely important. So just like with enthalpy, with entropy, it's the same thing. So if I said that I want to know I can say that S ref at T is equal to 0.01 and P is equal to 1 atmosphere is equal to 0. Okay, so then what I've gotten here is I've got, I have as a function of temperature in S, I can say 0.01. This is equal to 0. This would be joules per mole Kelvin. And we'll go over in just a second how we do the same thing with enthalpy as we do with entropy. But if I have an expression right, where I can calculate delta S is equal to some function that I'm going to manipulate, that we'll go over in just a second. This is equal to S of state 2 minus S of state 1. If I choose state 1 to be my reference state, then it's quite trivial for me just to say then, okay, this is 0, so that means whatever S2 I calculate is the same as my delta S. So far, we've only gone over how to calculate changes in enthalpy and changes in entropy. But by formulating it like this, it's the same thing, right? So all we have to do is choose a static reference state, and then from there, build everything up from changes in delta H's and delta S's. Okay, so let's go over real quick calculating entropy changes, and then I'll go over a little bit more clearly what I'm looking for in question 5. So for entropy changes, it's actually easier than enthalpy. So ds is equal to C sub p over t minus dv dt. It's a much simpler expression, which kind of makes sense because enthalpy is something we just kind of made up. But entropy itself is sort of a fundamental base function of the universe. So it's actually quite nice to work in entropy. So if we break it again into our steps 1a, 1b, and 1c, dsa is equal to minus dv dt at constant p dp. Right, this is our, we draw our PT diagram here, right? PT, we're going from here to there, so we're going 1, 2, 3 steps. So the temperature's constant. Then for 1b, dsb is equal to C sub p star over t dt. And remember that this C sub p star is a plus bt plus ct squared. So when you divide the whole thing by t, we get a over t plus b plus ct. Then we have to integrate this with respect to dt. So this right here will give us a natural log type function. Is this familiar to most people? Who's seen this before? From your undergraduate class, calculating delta S's for an ideal gas? Some people, or are people just being shy? This is something that almost every chemie undergrad class should have covered pretty extensively. Is everyone just being shy? Okay. So most people have seen this, I'll gather. And then lastly, for the last step, it's the same thing as the first, but just different limits. Okay, and I'll just throw it all together into one big equation. Delta S, which is equal to S2 minus S1, is equal to P1 T1. Minus, that is. broke it into 3 different steps, and now I just inserted the limits of integration and integrated it. So we have to use this here for a number of different problems. For problem 3 and problem 5, we have to use this. But for this homework, we're going to ignore the complex parts, the dP and dV parts. We're only going to worry about integrating the ideal gas heat capacities. So in terms of the entropy and everything like that, we're only going to worry about that portion of it. So so in question, let's see. Let's go over question 5 real quick. So question 3 is an adiabatic mixer, which is a fairly common unit op process. So that some people might have more background on that. But on question 5, what I'm sort of looking for here is I'm looking for a table that has temperature. I have H hat of the liquid, delta H vap, H hat. Actually, rather, I'm looking for more of a, I'll do the underbar to keep my nomenclature constant, because I want this molar. Then we want S of the liquid. We want delta S vaporization. And we want S of the vapor. And we want the delta G of vaporization. It's not as bad as it seems, I promise. So we're going to start off with our reference state, 0.01. We're going to call this 0. We're going to call this 0. So we're walking along a path of data that we have, and we're going to fill in this whole table with what we've done in class, and one other extra thing. So it should be straightforward to calculate all the way down from here to the 110 degrees Celsius. This path here is just the C sub P dt, right? We're just going to integrate from our reference state of 0.01 degrees Celsius, go all the way down to 110. So every formula that you put in this Excel spreadsheet or MATLAB code is exactly the same. Right? You've got a correlation here for your heat capacity. The only difference that changes is once you integrate it, your upper limit has changed. Okay?
Lower limit is the reference, right?
Lower limit is the reference. It doesn't have to be. If you really wanted to, you could sort of have it be the cell before it. But it all works out just fine, the math. So you could either calculate, for example, from here to there, from here to there, from here to there. Totally fine. That's the way that I would recommend doing it. Or you could calculate from here to there, and then there, and then there, right? Either way is totally okay. Or some combination therein. Whichever is the simplest to program up, I'd recommend doing that. Because we have a tool to calculate delta H's. So we're going to start off with something that we know, and the only thing that we know at the beginning is our reference state. So you have to start off at your reference state and branch out from there. But as soon as you start filling stuff in, then you can start mixing and mashing. Okay, so the next step then is we can do the same thing for the entropy and fill that in. Because again, in this case here, this is just C sub P over T dt. We're integrating that expression. Same thing, except it's a slightly different application of the correlation. You're dividing by the temperature and then going through the process of integrating it. The next piece of information you're given in the homework is the delta H of vaporization at 110 degrees C. The delta H of vaporization is a function of the temperature. So we have to go through a path that we know. In that case here, we know delta H of vaporization at 110 degrees C. And this is where we're jumping ahead a teeny bit, but I don't think it's too much of a stretch. Delta H of vaporization is just defined as the H of the vapor minus the H of the liquid. Final state is the vapor, initial state is the liquid. Why isn't it the other way around? Well, that's just because how we defined it.
I mean, it's, yeah, vaporization.
Exactly. So you could say the delta H of condensation would just be going from a vapor to a liquid. But it's just, I don't know, everyone thinks it's easier just doing it this way. So from there, we should be able to calculate the H vapor at 110. Right? Any questions so far? Then we could just march our way back down. And then we can fill in this information by relating between those calculations. Now, what makes this tricky here is I didn't actually give us any information about the delta S of vaporization. This is where I have to throw in a little bit of stuff that's maybe 2 lectures ahead of the game, but delta G is defined as delta H minus T delta S, which is equal to 0 at a phase transition. So that means we know delta G, we know delta H, we know the temperature. That means we can calculate the delta S of vaporization using our delta G formula. We're all on the same page? So that gives us the ability to fill in this spot in the table because we know that the delta G of vaporization is 0. So then we can calculate the S of the vapor, go down here, and then again fill in all the parts in the table, like so. Then we can calculate the delta G of vaporization by looking at the delta H of vaporization, the delta S of vaporization, and the temperature at which it's occurring at. It should be equal to 0. I didn't get 0. Actually, I was surprised how far off the calculations were. So this should be 0 all throughout, right, if our numbers are good. But based on the correlative data that I found and the number crunching that I didn't get it to equal 0. In fact, it was a lot worse than I thought it was going to be. So that either means I made a mistake or the data is just not as accurate as I was hoping it would be to do this calculation. I think I got something on the order of like 10 here. Let me think, do I have it here? Yeah, I got, so just to give you guys a fill-in, at 0.01, I got 10.3. I think this is kilojoules per mole, which is, I thought it was not very good. So I might have an error in my code, but let me know if you guys get a similar number. It should be equal to 0 according to thermo, because the delta G at a phase transition has to be equal to 0. But it just could be that we're asking too much of the data tables that I was looking at. Okay. So with this information, everything on the homework should be doable based on the theoretical content that we covered in class. But again, we're not going to do too much number crunching in the class, but we'll go over the math specifics itself. But in office hours, we'll go through all the number crunching that you want. And I've never turned a student away by emailing me and they say, well, what did you get for this question here? I've never turned anyone down and said, well, work on it yourself. No. So if you have a question on the homework, you want to double check your work, let me know. I've never turned anyone away because I really appreciate when you guys reach out and sort of double check your work because it shows that you're invested in the class. So I'm not going to kick you to the curb if that's the case. All right? Yeah, question?
Do you just want us to print out the table?
Yeah, that's what I do. So let me show you, I can just show you here what I do. So for example, on this problem here, number 5, I don't know if you guys can see it super well, but I basically break it down. Okay, this is how I'm calculating delta H. Here's the formula. Here I'm calculating delta S. Here's the formula. Here I'm calculating the heat of vaporization. And then I'll just give you the data tables. So in my handwritten work, I don't really have any numbers too much so. But I mean, I'm not getting graded as well. So the more you give me, the little bit better. But you don't have to, crunch. You don't have to do it by hand by any means. So I just put the generalized formula here, and then I have an extremely well-formatted spreadsheet that tells me the results of the calculations. But again, when it comes to homework and the same thing with exams, it's a balance, right? If you're working on an exam, you can't dot the I and cross every T for every single calculation, otherwise you'll run out of time for the exam. But if you skip too many steps, it's hard for me to give you partial credit. Same thing with the homework. So it's a balance of what do you think is an appropriate amount of work to show and what is not. But in general, if your work is extremely well organized, then I'll generally give you the benefit of the doubt saying, okay, yeah, they're clearly thinking through this process the right way. But there's no right or wrong answer as to how much or how little work should be shown. Yeah?
One thing I just was going to say this on, like on number 3, so I tried to problem 3 different books with 3 different values for the heat capacities, for the ideal heat capacities, and I've had numbers that range from like 5 to 6.8 to 6 point, and I think one of them was like 6.1.
That far off from different heat capacity data?
Yeah.
Oh, wow. Yeah, so I'm using the numbers in the back of the Sandler book. The one that I recommended for the class. Yeah, so I got, five's what I got, unless I made a mistake. But you're getting around that same mark, but just it's varying based on your data source.
Yeah.
I'm surprised it varies that much.
Like one of them has got like it's just weird. Like one of them is like, I think for the methane it's like 19.25, and then one of them is like almost 20 for the starting for the A value.
So it all depends. So it could depend on a lot of different things. So there's different forms of the correlation. Some of them will be A plus BT plus CT squared plus DT cubed. Some of them will have 1 over T to the 4th. So there's different correlations. Some are in Celsius, some are in Kelvin. So I don't know. It might be just mixing and mashing. But it also could be possible that the data is just not very accurate. I don't know how consistently accurate the data tables in the back of textbooks are. They're good for instructive purposes, but I'm not sure if they're good enough for like design purposes.
Might just want to go to NIST.
Could try that, or just let me know and I could just send you the data tables if you don't have the Sandler book. I can just take a cell phone picture of it and send it to you.
All right.
Yeah. Okay. Have a great weekend. See you on Wednesday.